All right, today I just want to finish up what we were discussing last time with this concept of either what we call differentials or linear approximations, because they both basically accomplish the same thing. Again, I'm going to stress differentials today because to me that's the more, both of them have some calculus involved in them, but differentials is a lot more efficient as a way of solving these types of problems. Okay? Differentials can be used to answer questions like this. It's a little bit of an outdated question, but the concept of showing how differentials works very nicely here. What if we want to approximate the value of the square root of 23, and I don't let you use your calculator to do this? Okay? Now this is, like I said, a long time ago before we had calculators, this is how they approximated values such as the square root of 23. Okay? How can we go ahead and use differentials to make this approximation? And then when we're finished, let's just look and see how close the approximation really is. We'll use our calculator and just see what the answer is. Okay? Now, if we want to approximate the square root of 23, there's two things we have to decide. First of all, what's the initial equation we're going to use? Well, we're looking for the square root of some number. So our equation is just y equals the square root of x. The second thing that we need to decide is we need to pick a nice value that we know the square root of that's really close to this one. And so what's the nicest choice we can pick? 25. So I want to use the point x equals 25, and then what's the y value here if I sub in 25? I get 5. So I want to use the ordered pair 25, 5 as my starting point. Okay? And basically what I'm going to do is I'm going to write a linear approximation for this equation at 25, 5. And then we will use that equation to go ahead and do square root of 23. All right, here's how differentials will solve that problem. What is the derivative of this function? Okay? Well, the derivative of the left side is just dy dx. The derivative of the right side is 1/2 x to the negative 1/2. But what we said the other day was with differentials, we have the ability to kind of multiply that dx across the equation here. And so we have dy equals 1/2 x to the minus 1/2 dx. So we kind of split apart these rates of change over here. Okay? All right, now what are the values that I want to sub into this equation to be able to figure out what dy is? Okay? Well, what's the x coordinate that I care about? I care about x equals 25 because that's the nice point that I started from. Okay? So I sub in 25 here. Now, the other thing I need to sub in is I need to sub in a dx. Okay? And the question is, if I start at 25, how much of a change in x needs to take place before I get to the number that I really am interested in? -2, because I started at 25 and my change in x went down, my x went down by 2 units, right? So my change in x in this problem is -2 because I'm going from 25 and I'm going down to 23. Okay? All right, now if I go through and calculate this, okay, 25 to the negative 1/2, that would be 1/5. 1/5 times 1/2 would be 1/10. 1/10 times 2 would be 1/5. I think this answer is negative 1/5 if I did that correctly. Okay? If I didn't, let me know. All right. So what this is saying is that if we let the x change by -2, in other words, if I let it go down from 25 down to 23, how much does the y value change by? The y value changes by negative 1/5. So what is the new y value that we expect this to be here? If I just lose 1/5 of a unit here, where am I at? 4.8, right. Okay? So our prediction for the square root of 23, our prediction for that value is 4.8. Okay? Because what we did was we go ahead and plug in the x the nice x, we plug in how much the x is changing, and then that tells us how much the y coordinate's changing. Okay? And then from there we can just go ahead and make the adjustment off the y coordinate. Now my question is, what is the square root of 23 if you sub it in your calculator? 4.79? Okay, so this is a pretty good approximation. 4.8 is a nice approximation. And notice we didn't have to use any calculator function. Again, it's not that if we got calculators, we want to use them. I mean, that's obvious. But the idea is that if we get to more complicated situations than this, using computers to do calculations for us, it is much faster for a computer to calculate something in this form, which was more of a linear form, than it is in like a square root form, or a logarithm form, or exponentials, or trig functions, or whatever it happens to be. Okay? And so that's the real advantage of differentials here. Okay? So there's one type of problem where we could use differentials to solve. Here's another type of problem. I'll put it up here on the overhead. Maybe I'll put it up here. Okay, this number 17 right here. It says the demand for grass seed in thousands of pounds at a price of X dollars is given by this equation. Rats. Okay, we'll try this again here. Maybe I can do this. There we go. Okay, so we've got this equation. It's a cubic equation, but it says use differentials to approximate the change in demand for the following changes in X. And letter A says we want to start at $2 and we're going to change up to $2.50. Okay, so what if we change the price up by 50 cents? How does that affect our demand? Are as many people going to want to buy this if they have to pay 50 cents more? Okay, all right. So our initial function is just d equals negative 5x cubed minus 2x squared plus 1,500. All right, I want to use differentials to do this calculation. Okay, so I need to come in and take a derivative. Okay, just like we've already got our initial equation here. Okay, I need to come in and I need to take the derivative. All right, so what is the derivative of this left side here? Okay, this is going to be a little bit confusing. If this would be a y, what would be my derivative over here? dy dx. Okay, this is a little confusing because this is already a d. So what's the derivative over here? dd dx. That's why I said it's a little confusing because d stands for derivative, and then d also stands for the demand of this problem. If you want to change this to a y, you can. I mean, it's not going to matter really in the big scheme of things. All right. What's the derivative of negative 15x cubed? All right, I just gave away part of the answer. Negative 5x cubed. Negative 15x squared. There we go. Okay. Derivative of negative 2x squared. Negative 4x. Okay, and then again, the idea of differentials is I can multiply that dx across, and so I get dd equals negative 15x squared minus 4x all times dx. Now, the only two things that we have to identify to figure out how much the demand is changing, I need to figure out what was the x that I care about, where am I starting at, and then how much did it change. Okay, so where am I starting at with x? Starting at $2, and how much did it change by? 50 cents, right. So I just sub those two numbers in. Okay, negative 15, $2 squared, minus 4 times $2, and then all of that times 50 cents. Okay, this is 4, negative 68, negative 68 times a half, I think it should be negative 34. Okay, and again, if I did that wrong, correct me. Okay. So this is how much the demand is changing by. Okay? And is that what they're asking for in the problem? And the answer is yes. Use the differential to approximate change in demand. And that's exactly what we've got. The change in the demand function is negative 34. Okay? What this is telling us is that if we were to go back, this is one way to, this is the way to answer the problem using differentials. What this is approximating for us is if we went back into the original function and we subbed in x equals 2 and got an answer, and then we subbed in 2.5 and got an answer, and then we figured out how far apart those two answers were, they should be pretty close to this much apart. Okay, the second answer should be 34 less than the first answer. Okay, that's what this is approximating for us. All right. So that takes care of 17. Now let's go look at this next example. Okay, 28. It says an oil slick is in the shape of a circle. Find the approximate increase in area of the slick if its radius increases from 1.2 to 1.4. And again, the key, notice in here they talk about find approximate increase. So we're just estimating or approximating this value. Whenever we're just approximating a value, we can go ahead and use differentials. Okay? Now, the difference on this one is they do not give us an equation to begin with, but what does it look like the equation should be related to? Yeah, it's definitely something to do with a circle, and then what do they want us to find at the end of the problem? Find the approximate increase in area. So that, put those two things together, we need to write the equation for the area of a circle. And what is that equation? Okay. Area of a circle, pi times radius squared. So this is the initial equation that we start with. Now, if I was to give you this, and I was to give you problem number 28, could you use differentials to solve it? Okay, and if you answer that yes, then you know what you're doing here. Okay. Now, question is, what is the derivative of this function? Well, what's the derivative over here? dA dr, because r is my variable on this side, so that's my independent. Okay. What's the derivative over here? Okay. Yeah, and that's it. Okay. Just 2 pi r. R is like my variable, so it's just 2 pi times r to the first. Okay. Differentials allows me to multiply that dr across. 2 pi r dr. Okay. And again, if I'm interested in finding the change in area, the two numbers that I need to know what's the radius we want and how much did the radius change by. Okay. Well, what are the answer to those questions? What's the radius we want to start with? 1.2. And change is how much? 0.2, because it went from 1.2 up to 1.4. We plug this in our calculator or just multiply it out here, whatever, and we come up with the amount of the change in area. Okay? All right, so there's that example. Let's do one more here, and then we'll call it a day. Okay, let's look at 34. It says the edge of a square is measured at 3.45 with a possible error of plus or minus 0.002. Estimate the maximum error in the area of the square. Okay, this happens a lot in the assembly line type world where things are measured. You have a drill press or something that's supposed to be drilling a hole at a certain spot or at a certain size. But yet there's always the possibility for error. Maybe the setup is just a little bit off. Okay? Or maybe the drill bit is just a little bit too big or too small. And so they always allow for this possible error in there. And so then they want to know at the end of the problem, well, how much, in this case, how much error could I have in the area of the square? Okay? All right. My question is, what equation do we need to start with in this problem? Area of the square. Sure. Okay? And what is the formula for area of a square? What's that? Yeah, it's just s squared. Whatever our side length is squared, because it's just side length times side length, because they're the same value. Sure. Okay? So now I want to go through and use differentials to calculate this. All right? What's the derivative of the left side? dA ds, derivative of the right side. 2s, I multiply the ds across, so 2s ds. And again, not that this is really difficult, but just notice how all these problems are following basically the same pattern here. Is we have our dA on one side, we know what we're solving for is on one side, and it's just a whole bunch of multiplication on the other side, isn't it? Just a bunch of stuff multiplied together. A lot of this can be done very quickly on computers because multiplying numbers together is a very slow or a very easy thing for a computer to do. It's very fast. Okay? All right, what's the side length that we care about here? 3.45, sure. And how much of a change from that side length could we get? plus or minus 0.002, right? Okay, we could be off from this number by 0.002. And if I go through and I multiply this out, I'll get a plus or minus type answer because I might be, the area might be a little bigger if this is a bigger value. It might be a little smaller if it's negative 0.002. Okay? And you just multiply this out and see what that value is, and that's how much the area could be off if the side length is off by 0.002. Okay? All right, any questions with this? Differentials is actually not a really difficult concept to grasp. Okay. Have a nice spring break, and we'll see you back here in a week or so.